Okay, welcome. I have a fairly bad cold, getting better. I will apologize in advance for coughing through the class. I will try to minimize that, but as you can see, I'm not doing super well with that. So hopefully this class is not too annoying. But let's get through modeling mechanical systems. But last time we did translational systems. This time we're going to do rotational systems, and it's all going to be the same concepts. We have inertia, we have springs, and we have rotational dampers. We're going to do the same concepts. We're going to use slightly different terminology because now we're rotating. So the first one we'll start off with is inertia, and we have to have a rotating mass that mass is going to be accelerated. And as we accelerate the object, what we end up finding is that it takes a lot of energy to get that mass rotating. Once it's rotating, then you don't need to get as much as much energy into that to go ahead and do that. And so the way we characterize that is our torque, because we're not talking about force anymore, right? The difference between force and torque is subtle, because you can apply a force to a rotational object, but if you push on something perfectly in line with the center, it doesn't rotate. So the torque is going to be you looking at things as a function of the angle that you're applying it at, as well as the distance away from the shaft, right? Torque is force at a distance, essentially. So it changes things a little bit. So we use torque. And so our torque equation is going to be equal to J, which is our moment of inertia term. And again, it's acceleration. It's multiplied by acceleration. We're going to do things in class, just to simplify things, as a function of position. And so we're no longer looking at the distance from something, because it wouldn't make sense to have a nominal position to say that this is the zero position and then keep track of the distance. It would always just keep increasing and increasing. It wouldn't be any value. So what we do is we use angle. And we start at 0, we work at 360, and then we just start back at 0 again, right? So we just keep repeating that point if we're trying to track it. So we're going to use theta as our measure for how far something has rotated. And we're taking the second derivative of theta because that's our acceleration. We take that into the Laplace domain, multiplied by a constant is multiplied by J. Second derivative is multiplied by S squared. And we have our theta S, right? That's the inertia term. A damper. We do have dampers, and they're pretty easy to make, just as rotational. So the ports, instead of being lined up when an object is moved in this direction, it would be sort of as the object is rotated around. So it's almost like a paddle with some holes drilled in it. So it'd be sort of something that's spherical in design, and you just port oil in that direction. So exactly the same constant for concepts where you have that oil that is going through the ports, and that would be viscous, which is another way of saying fluid, viscous friction. So again, we're trying to do a similar things what we did for linear systems. We're trying to do force balance, so we have to calculate the amount of torque that is required to get that damper moving. And if the fluid is rotating along, the only time you're going to get more energy or more torque required to rotate that is when you're trying to rotate that internal damper faster than what the fluid is rotating at. So that's a velocity term. If everything is flowing at the same rate, there's no fluid that's going through those ports, then you're good to go. So the velocity is the first derivative of position. So we go B times theta, first derivative of theta. We take that into the Laplace domain. Our torque is equal to B times S times theta S. And again, here it's proportional to angular velocity. The last one we have is a spring, and these are much harder to physically understand. They do exist, but they're kind of limited in terms of what they do. The ones that I've seen, rotational springs, if you can envision this, they do make washers that are not flat. They kind of have a spring associated with them. And what I mean by that is they kind of look like this. They have ridges like that around the washers. And as you apply a force, as you rotate the object, you tend to move the shaft. It would move axially along the direction, one direction or the other. And it depends on how the motor is rotated or the unit is rotated. And that will push down on these things. And because that metal, that washer is a springy metal, those end up compressing. Okay. So they only will compress based on how much that shaft is being pushed against it. So that's the same thing as much as I move my position, we go ahead and move that. So this spring, the torque that's required to go ahead and compress that spring is based on the position times theta t. So my torque there is equal to K times theta S. And again, it's proportional to the angle. So those are the three equations that we have to do. Everything else that we do for analysis in terms of torque balance or force balance, depending on your perspective, it's exactly the same. All right, so let's start out with a simple system. Here's our system. We have a moment of inertia here. We have a damper. And we have a spring. And you can see that my force is being externally supplied, right? You can see the torque is being externally supplied and it's forcing it to rotate. And I guess if you stand here, it's going in the counterclockwise direction. So the way that I do these is instead of a point, like on a free body diagram, I just show it as a line. And now I do my torque balance this way. So my first torque is my applied torque there. Now, the moment of inertia, it is taking energy in to go ahead and accelerate or store energy in the mass to go ahead and rotate it. So that torque is going to be in the opposite direction. That is opposing my applied torque. So it's going in the clockwise direction, opposite of what we have. Let's do the damper. The damper is the next item. And again, it is only going to oppose a force when it's being forced to rotate faster than what the oil is inside of it. The oil wasn't rotating, we're going to assume. So that force is there. I called it Che. I meant to say V, sorry. And finally, the spring is at equilibrium. We're assuming, that it's at a happy state. All of a sudden, we're trying to rotate it. The spring doesn't want to go in that direction. It wants to stay in equilibrium. So we have a torque in the opposite direction. And this shaft position here is tied to this shaft. This spring and this damper are being rotated at the same rate. So this is the position of this shaft, right? Because it's all connected to one mechanism. That's theta. The relative position, this is the other position here. Whoops. This position we're assuming is 0. This is a stable, non-moving point. So it becomes a 0 point. It's our reference point. So when we calculate what our relative position is for the spring, one is not moving and the other one is being rotated at theta. With the damper, we have to pick a starting point. So we'll just assume the velocity of 0 because we don't know what the previous velocity is. We're just going to assume it's 0. So our position is theta minus 0 is how we calculate the position. So when we take the derivative of that, it's just d theta. Or if we take the second derivative, we just have the second derivative of theta because it's the second derivative of 0 is 0. So now we can do our force balance. Here's our applied torque. Here is T sub J. Here is T sub B. And here is T sub K. Those are the three torques. And they're in the opposite direction. So this is the, we can say that this is we'll call it the counterclockwise direction. And these are the clockwise direction, assuming we're looking from that perspective there. You could also put them on the same side and set them equal to 0 if you want, but just make sure you keep track of the pluses and minuses and directions. Everybody understand how we're adding those together? Okay.
Paul, I just had a quick question though.
Yeah, go ahead.
It's not too bad. Is there a reason why theta is just represented differently in our Laplace transform equation, or
It's just capital. If you
just
remember,
capital?
if you remember when we're typically, let me just double check to see. Oops, let me just check. I just want to make sure I'm recording. I think I am, but I think I saw the button here. It's really slow. Yeah, it's recording. Okay. So in the time domain, we use lowercase letters, so it's f of t. In the
Yeah.
Laplace domain, we use uppercase letters. So that is the uppercase theta.
Okay. I've just
to,
never seen it before.
Yeah, it's a weird symbol, but we're trying to distinguish between lowercase and uppercase to show that one's in the Laplace or one's in the time. It's more important when we just say this is f and this is f. If you know about control systems, you realize that this has been converted to the Laplace domain. That's the reason why we try to keep it consistent. Even the T
Gotcha.
equation, you notice T, that's the capital T for the torque. So
Yeah.
just trying to be consistent the way through.
Gotcha. All right. Thank you.
Yep. All right, now we can factor out our theta s. We saw for our transfer function, our input is our applied torque. So this is the input. Our output is our theta position. And now we can do our block diagram. 1 over js squared plus bs plus k is our block. Questions on that, Avery? Because the torque applied, you're forcing it to rotate. The other torques are saying, I don't want to rotate. Okay. I'm happy to stay where I am. Right? It's like the moment of inertia. Something is not moving, but it's got a mass. Now I have to rotate it. I have to put more energy in to get it to rotate. It's the same thing with the damper. I'm happy being not moving at all. Now you're forcing me to move, and this oil is not moving. So now I've got to have an opposing force. And the same thing with the spring. Spring was perfectly happy sitting in equilibrium. Now you're forcing it to rotate. It doesn't want to rotate. It wants to go back to its nominal equilibrium position. Okay, here's another example. And a little more complicated because we have two masses with a spring between them. And these items can float relative to each other, right? So if you look down over here, we have a couple of bearings over here. We have a shaft, and we're going to assume that these are frictionless, kind of holding the shaft in that center position. So we're going to go ahead and apply a torque to get that to rotate, and then we're going to see how we can come up with a transfer function to go ahead and relate that. And so now we have a theta 1 and a theta 2, which means this might be a good one to use the multi-input, multi-output, or single input, I should say, multi-output approach to doing that. All right. So we're going to have to do two torque balance conditions. Let's go ahead and do our first. And so this is going to be for mass J1. So we got a torque that's applied. I've got to rotate J1, right? J1 is going to be rotated, and it's going to be relative to a nominal position of 0. That's going to create an opposing torque. Call that J1. We also have the damper over here that, again, is going to oppose any change in motion. That's going to be B1. Now, this is the harder one, right? I have a spring, and it's between two objects that can rotate freely. So how do you calculate the torque in the opposing direction? Remember, this torque, this spring doesn't want to change its position. It wants to stay where it is. You're trying to get that to rotate this way. So how do you get a torque in the opposite direction? Well, if theta 1, which is the angle associated with J1, is moving faster than the object at the other end, the spring is being elongated, which it doesn't want to do. It wants to stay in equilibrium. So this is going to be proportional to theta 1 minus theta 2. So here's my applied torque. Torque J1, torque B1, and torque of K as a result of the fact that theta 1 is going faster than theta 2. Make sense? Let's do the second one. J2, any applied torque? Nope, nothing externally coming in, right? There may be an external torque coming from something else, but we don't have to worry about that. So there's no applied torque. Where are our torques? Remember, it's an equilibrium point. So if something is being forced to rotate in the, I guess if we're looking over here, that's in the counterclockwise direction, this torque wants to operate in the opposite direction. So we have torque B2. Now the question is, what is the theta? What is the speed? Well, if you look over here, B2 is sitting against a stationary object. It's not rotating. But the damper inside is rotated to an object that's rotated at theta 2. So this is proportional to theta 2. It's not theta 2 minus theta 1. It would only be theta 2 minus theta 1 when the damper is between two rotating objects. But because BT is stationary, it's only theta 2. Same thing with J2. It's just a moment of inertia relative to a non-rotating turn. Now I got a spring. How do I do? Let me put my TK over here. What would that be proportional to? It's theta 2 minus theta 1. And the reason why is because if theta 2 is spinning faster than theta 1, the torque is going to be in the opposite direction, right? If this is going faster than this, so they're both going, but this one is going faster. Can't rotate my hands this way. So if this is going faster than this one, the spring is going to want to try to slow it down. So this is proportional to theta 2 minus theta 1. Causes an opposite direction torque. So here is my applied torque. There's no applied torque. Here is my J2. Here is my B2. And here is my torque. Notice it's theta 2 minus theta 1, opposite direction. All right, here are my transfer functions, just taking the Laplace domain. Hopefully you can see they do this pretty quickly. Now I go ahead and I set those up into the single input multi-output system. And then I can write it as alpha, beta, gamma, and lambda. And again, if you have had linear algebra, this might make a lot of sense, but this is using method of cofactors to solve for these parameters. If it's a 2 by 2 matrix, it's actually really easy. Does anybody know method of method of cofactors? Where anybody taught how to handle, how to do take an inverse of a matrix without actually, by doing it by hand? Nobody? It's okay if you haven't, that's okay. You have a calculator to do it, but this is just a way that you start canceling terms out, and it's, you know, I don't know if you have to do it all because your calculators can do it pretty well for you. Move this up out of the way. Whoops. And so now you can see the delta term, which is what's in their denominator. And then I have my transfer function, theta 1 over tau, which is our input. So this is my input. This is my output for the first disk. And this is my input or my output for the second disk. Those are my two transfer functions. Questions on how to do those? Everybody afraid to ask a question or kind of making sense? Great. So let's throw in some gears. Is that a big deal to throw in some gears? We already talked about it in class before. A gear is just a transformer. All it does is change the speed. Which one's spinning faster? N1 or N2? Why? Smaller gear, say more. Yeah. This one right here has to keep up with the rotation of N2. So this one's going to be spinning at a much faster rate to kind of maintain, you know, being in lockstep with N2. So N1 is spinning at a much higher rate than N2. But the downside of that is N1, because it's spinning at a faster rate, doesn't have as much torque as N2. Why is that? Because power is equal to torque times omega, right? Omega is rotational speed. If I increase the speed, my torque had better drop down. Why? Because power is constant. Unless I'm putting in external power from some other place, which I'm not, and we're assuming that we're not having any losses in our transmission or our gearing system, then the torque has to go down because the power has to remain constant. Okay? So that's why you start your car. I don't know if anybody has a manual transmission vehicle anymore. Anybody? Nobody? It's okay. You don't have to, but back in the day, not that long ago, actually, and maybe if you drive sports cars, you'd always start your car in first gear, right? Why is that? Because you have more torque. Why do you need more torque to start your car? It really lends itself well to what we're studying. Yep, say more. Why? You guys are saying it, but you're not exactly saying it. You're starting from a dead stop. Why do you need more power? Thank you. Your vehicle is completely stopped. How much energy is stored in a moving vehicle that's not moving? Zero, right? So if you want to get that to 25 miles an hour, that car that has no stored energy now has to be moved and accelerated to get to 25 miles an hour. It takes a fair amount of energy to go from 0 to 25. Once you're at 25, it's much easier to maintain it because you have some friction with the tires and you have some wind resistance. But the reality of it is like you don't have that inertia to maintain that anymore. You're already at 25 miles an hour. So, and we talked about it, you let off the accelerator. So you start in first gear because you need a lot of torque. That's all it is. That's exactly what we're talking about in class. So with gearing, geez, sorry, thought I was doing okay. With gearing, you have to use a lot of gearing. In a lot of cases, you'll find motors operate much more efficiently at higher speeds than at lower speeds. But if you need more torque, you can step down to a much lower speed. I'm sorry, you can step down the speed, you can step it down, and then you have a lot more torque available to you. So what we'll do is we'll set our equation based on distance traveled, right? The distance traveled is the same. So theta 1 times R1 has to equal theta 2 times R2. And then we'll just do some math. We'll say R1 over R2 is equal to theta 1 over theta 2, which means N1 over N2, which is our turns ratio, right? It's our gearing ratio or turns ratio. But the work is the same. So we know that the same amount of work has to be done if we're assuming that the transmission doesn't have a lot of losses and we're not putting any energy. So the work is force at a distance. So torque times theta. So we have torque equals torque 1 times theta 1 is equal to torque 2 times theta 2. That's going to be equal to N1 over N2. And so how we take our torque up or down is by turning our turns ratio, if we want to simplify it and assume it's a completely lossless system. So you can see that in this case, the N2 looks like it has more turns or more teeth, right? Whereas N1 looks like it's less. So we see that the torque on 1 is going to be lower because the number of teeth on N2 is greater than N1. So this is multiplying by a ratio which is less than 1, just based on what we see in the picture. So the torque here needs to drop because the speed has increased, which is exactly what we said there. And that's the basics for transmissions. All right, your turn. Give you 5 minutes. Try this system. You guys try that system. I'm gonna see if I can go find a tissue.
For the first one, I haven't done 3 yet. For that first question that has the 2 options. Yeah. Is that it? Am I overcomplicating it? It's not the same thing he does in the video, where he puts like, you know, but it's like T1 just times T2, right?
Remember, just draw, get started if you're stuck. Draw whatever mass you're trying to accelerate. And then start to apply the forces. You'll note that the torque here is applied sort of in the middle between J1 and K, which is between J1 and J2. Couple more minutes. Think about where your zero positions are. You have a brick wall here, so that's zero speed. That's zero speed. Moment of inertia always has to do reference to zero. So this is going to be, these three, I should say, are all going to be reference to zero position. But the springs and the K and the damper in the middle, you need to calculate those based on a difference of position of two objects that can rotate at different rates. All right. Let's see how we did. Anybody get that for mass number one? Your torque is applied right here. That's in that direction. So this is my applied torque. Here's my J1 torque, my D1 torque, my damper. Hopefully you can see those pretty easily. The next one is, which one is moving faster? If one's moving faster than the other, it's going to oppose. So if I assume J1 is moving faster than J2, then the torque is going to be in the opposite direction. So for this to be in the opposite direction, it has to be proportional to theta 1 minus theta 2. Anybody get that first equation? Good. How about the second one? Here's J2. No applied torque. So all the torques are going to be opposing. Let's do the easy one. That's J2. That's pretty much the only easy one, right? Because the other two torques, the damper is not is between two rotating parts. And again, the damper is going to be causing an opposing torque if if the theta 2 is rotating faster than theta 3. So this is D2, which is proportional to theta 2 minus theta 3. And then the last one is my K. And that's going to be proportional. It's going to be opposing torque if the disk theta 2 is rotating faster than theta 3. So that's K, which is proportional to theta 2 minus theta 1. This might have been the most difficult one because you have the two that are relative, relative speed changes. And then the last one, here's my J3, no applied torque. So we know J3 is always relative to that position. D2 is between, D2 is between theta 2 and theta 3. And again, if theta 3 is moving faster, it's going to try to oppose that torque. So here's D2, which is proportional to theta 3 minus theta 2. And then my last one, which is D3, and I'll just put it up here. It's just going to be theta 3 because one object or one part of the disk is relative to 0. So that's just going to be proportional to theta 3. And those are my three masses. Now, I'm not expecting you to do transfer functions for those because those would be a lot of algebra, which would be prone to making mistakes. But the process is exactly the same. You take it to the Laplace domain, multiply by S, and then you just move things around as necessary to get the outputs that you want. Let's apply that to an electrical system, which is a really easy kind of basic system, which is a DC servo motor. And we use DC because it really makes it more simple. And what we have with a DC servo motor is we apply a voltage here, plus and minus. And that voltage there, the whole purpose of it is to provide a current that flows in through this wire. And it creates a north and a south as shown in that direction. You notice that there's a little break. Anybody know why there's a break in between those? Why is there a break? The most obvious one, if this was just a continuous loop, you'd short V plus to V minus, right? So you'd have a short. But the other reason why you want to do that is because this winding over here, now you'll notice it's connected to the negative terminal. But if it's rotating, and eventually, let's just assume it's rotating in a counterclockwise direction, eventually this is going to be connected to V plus, and now the current is going to go in the opposite direction. And the reason why you do that is because in motors, you always want a swapping magnetic field because you see there's north and south here. At some point, the magnet inside there would be south-north and it would be locked in position. It would never change, right? So to keep that rotating, just when you're going to get the south and the north perfectly lined up, it should flip the direction. So you can see if we rotate it in this direction here, we're getting close to these lined up just as these two here switch directions. And so when they are lined up, now this becomes north and south. They oppose each other and then it keeps rotating. So this is a commutator with brushes. That's how they just slide along and they just come into contact. So to model this, we apply an input voltage, VDC, that's our input. And our output is either omega or theta of the rotating motor. Let's look at rotation. So now they're lined up. You can see we're perfectly lined up. North and south are there, but there's no current anymore. So the magnetic field drops out. Now we switch just to the case now where our polarity is swapped. Then we continue along. And we can see that rotated here. Okay, want to see that again? start here. Rotate. Now we just switching to the place where our north and south go. Our plus and minus go. Now we no longer have south and north lined up. It's north and south, so they are opposing each other. Forces it to continue to rotate. And then it just continues on that path. Here's just a couple images. And then here is kind of a really basic. If you can zoom in, these are pretty cheap, pretty easy to make. I mean, it's just a little piece of copper wire, so it's really simple and basic, but works really well. All right, so let's model that. See if I can move this over here. So we're going to assume a permanent magnet instead of trying to get fancy where you're going to assume that it has a constant field, just to simplify things a little bit. So this here is going to be excuse me. This is going to give us a constant magnetic field, that north-south that you see externally. And inside my motor where I run my DC, I have a resistor of the motor and an inductor of the motor. The resistance is because we have copper wire. The inductance is because we wrap copper wire around a magnetic core, and we have a bunch of that. This here is the output. This is what the motor is actually connected to. That's on the shaft, and that's what's being driven. That's the mechanical load that's being driven by this motor. So one of the things, and I don't know how much you've learned about this, but we don't want this mechanical system, we don't want that to be shown into our electrical circuit because it doesn't really make sense. So what we do is we have across the winding here, we're going to generate a voltage. And that voltage is called the back EMF voltage. And that voltage is proportional to how much power is going out of the motor. If the voltage is really small, then we're pulling lots and lots of power out of the motor because the current is really high. If the voltage is large, then there's hardly any current going through the system and there's very little load. And so that's called back EMF, and it helps determine how much current is flowing through the motor. So we're going to characterize that E sub M based on the amount of power that's going out of the machine. So now we can do just a KVL loop. We have a plus to minus voltage drop here, a plus to minus voltage drop here, and we have a plus to minus the back EMF voltage drop there. So we can sum our three voltages here. Our applied voltage is equal to the voltage drop across the resistor plus the voltage drop across the inductor, which is just L dt, plus the back EMF voltage. So now we'll take those to the Laplace domain, and we end up with just a simple block there. Our back EMF voltage is equal to some machine constant, and it's based on the rotational speed. Why do you think it's based on rotational speed? Right, we know that theta is position. Whoops. So the derivative of theta is velocity. Why is my back EMF proportional to the speed? Well, usually, not always, but usually the faster things are spinning, the less the load is on, right? If you have no load on something, it's spinning as fast as it can. If you have a tremendous amount of load on it, that thing is going to slow down, right? It might even stop depending on the load. So my back EMF voltage is going to be proportional to that, again, that K sub M, which is the machine constant, times the speed of rotation. So under very, very heavy load conditions, right, this voltage is almost zero. And under no load conditions, we'll say it's E sub A. There's hardly any current going into the machine, right? So no load is here, and heavy load is here. And so our equation EM is just a proportional. It's K times the velocity. So we take that into the Laplace domain. Our next equation is a way to relate torque. So our output torque, and this is again, without getting into a lot of detail, it's going to be some machine constant times the current into the machine. Take that to the Laplace domain. I have KT times IA. Now, what is the actual torque on the machine? Well, if this is a mechanical load and I don't have anything connected to it, it's going to be the moment of inertia times whatever friction I'm going to experience because I've got some bearings or whatever, or maybe instead of calling it friction, maybe that's the actual load is proportional to the speed. So this could be load, and this is my inertia. So the mechanical torque, the output torque that the motor is delivering is going to be the sum of those two. Take that to the Laplace domain. Here are the parameters to equate those terms, RM, LM, IA, EA. You can take a look and see what those terms are. All right. Now, at this point, it's just a question of writing a transfer function that relates the output torque, or position, I should say, to an input voltage. So we're going to do a little bit of massaging. So EA minus EM, this is from our KVL loop, is equal to that equation. I move my EM to the other side. Where's my stuff here? My torque is equal to this term here, which has equals, here's the mechanical torque, and that torque is going to be proportional to that constant there. So my input voltage is going in here. I run that through here, and then I've got my IA term. This is my IA, right? Because EA divided by this term becomes IA. Once I subtract EM, so this is EM, so this is EA minus EM. And if I take EA minus EM and I divide it by RM plus LM times S, that equals IA. So this term right here is IA. Now I multiply that by KT and I've got my torque. That's the torque that is actually going out on the shaft. I divide that by JSV, and that gives me S times theta S. What is S times theta S? Just omega, isn't it? It's the actual speed of rotation. And then I feed back in here K sub M, because if you recall, EM was equal to omega S, or omega of S, times that machine constant. And that's my block diagram for the motor. Don't see it?
No, just the speed, that's like it's just.
Oh, that's okay. But why is this cool? Because now I can take the voltage and I can adjust the voltage and I can determine the speed of rotation of this permanent magnet motor. Hopefully pretty easily. And I have a block diagram and I can pull out different points. If I want to monitor the current, I pull over here. If I want to monitor the torque, even though remember, this is a mechanical torque, so I can't really measure that unless I put some sort of a load on it. And anybody know what a mechanical load is? Rotational mechanical load? Maybe, but anybody here in the cars, how do you determine the output of a car? How do you determine that? But what kind of measurement device do they use? That's the unit, but how do you measure that? Not wheel speed. It's a dynamometer, right? Anybody ever seen they put cars on dynamometers? They strap down the front end of the car and then they put the rear of the car on this thing that can rotate. And then that's how they actually calculate the torque. They can put it on a dynamometer and they can measure the actual torque. So this would have to be measured with some sort of a dynamometer. We do have some in the lab that we can measure those, but this here is hard to measure. That's a mechanical torque. This is easy to measure. This is just a current meter, right? If you have access to it. And this is pretty easy to measure. This could be, you know, photoelectric device that is just getting a pulse of light and you can measure that pretty easily. This is almost impossible to measure because it's the voltage across the coil. So it's inside the motor, and it's just it's a motor that a voltage that's developed, but it's very, very difficult to measure. So almost impossible. Oops. If you wanted to get theta, you just integrate it one time. So if you actually want to know position, you would integrate it. The likelihood of you actually doing that is pretty nil. So most of the time, we really want shaft speed. Why do we care about the angle theta? Because it's always rotating along. Why do I want to keep track of that? But RPM, or radians per second, is a much more useful thing for me to use. So you can derive the transfer function for this. If you wanted to do the equations, you know how to do the transfer functions. It's just basically going to be I'm really not faking it. I don't know if people can tell, but it's pretty gross. So you can do the transfer functions. You have the block diagram. You can even figure out if B is small or L is small. You can figure out different characteristics. And you can actually simulate all this stuff in Simulate. Here's a transfer function. I'm not going to make you derive it because you can see this quite a bit. But here's the transfer function here. You can walk through the process if you really want fun. But that's the actual transfer function. And it's only a second order system. You can see I've only got an S squared term right here. Not too crazy difficult to find. Oops. Then you can simplify the diagram, and we'll get more into this as we start to look at doing block diagram math. But you can see blocks that are in series like these two. You can combine them just by multiplying them together. Because in the Laplace domain, it's just multiplication. So you can see that the KT is going to go in the numerator, and the LMS RM is going to be multiplied by JS plus B in the denominator. So pretty simple. Then this is the KM term that's in the feedback path, which if you have a feedback block, the way that you do this is my output Y, I'll rewrite that here, Y of S is going to be equal to my input R of S times G of S. That's the term that comes in over here. But notice there's also this term that comes back over there, right? So that also comes back, but it comes back as a negative. So that's Y times H times G. I'm going to bring that to this side. So Y plus Y times HG is equal to R times G. I'm just getting rid of the of S terms to simplify it. I factor out a Y here. 1 plus GH equals, whoops, I have X. I need my X term over here. X times RG. And then my transfer function, Y over X, is equal to, actually, no, sorry. My input is X, is R. This is my input. So Y over R, which is my transfer function, is equal to G over 1 plus GH. This is for negative feedback. And we'll be doing that a lot this semester, trying to understand that. So if you have this block here, this is my H term, that's my G term. You plug it into that, and that's how you can do it for this negative feedback block. So here's my block diagram, becomes G over 1 plus GH. So again, do some math. And we end up with, whoops, my overall transfer function here. Kind of a mess, but you would end up with that term there. You can see that this is G1 plus GH. And then you just have to do that math. So if you wanted to replace this whole thing with one feed forward block, that's what you'd end up over there. Questions? Because you should now have enough information to do the second homework, third homework, I think, right? What's that? Due Thursday. So do we want to start talking about an exam? Do you want to do one next week during lab, or do you want to do the week after? Say that again? It'll be, because that's a review, so we'll have some Laplace stuff, yep. What's that? Who would like to have it next, because next Wednesday? Loud and proud? 5, 6? How about in TV land? Let's do a poll. Let's see, I will edit this one. How do I edit it? I'll just create a new one. Exam 1. So that'll be the 19th, right? Or February 26th during lab. And let's launch it. Okay. So those of you in TV land, it'll be anonymous, obviously. So please answer. 1, 2, 3, 4, 5. Only 2 haven't responded. All right, February 19th, so a week from Wednesday. I will have to check with Mark. Mark will have to do the exam only because my dad has an eye appointment that I have to be there in Portland. So I'll have to coordinate with him. So unfortunately, I can't, it's at 1 p.m. So, and my dad is not doing great. So I have to be there for power of attorney. So I won't be able to be for the exam, but I'll make sure Mark has all the material and all that stuff. So I apologize for that. I hate to miss exams, but this has been something that was set up a month ago, and we tried to do it a few weeks ago, but they actually rejected him, so we had to go back to Portland, Augusta, never got served because it's just a whole mess. So, all right, so we'll do the first exam a week from Wednesday during lab. You get 1 note card, same as it ever was. I don't know if I'll be able to get them graded for Thursday because I'll have to coordinate with Mark getting the exams. I mean, I might be able to come back into campus that night because his appointment's at 1, so I might even be able to get back for the end of the exam, maybe. Depends how quickly his appointment goes, because if it ends at 2, I might be able to make it back to Orono around 4:30-ish. I think it's about 2.5 hours from Portland, give or take. So I might be able to make it back.
You're gonna give us that.
Yep, you have the Laplace table. All that good stuff. All right, any questions? So we'll do an exam review. We can either do it Thursday or we can do it Tuesday before the exam. This coming Thursday? That's okay. The only thing is, normally people want it to be right before the exam because they'll study and then they have questions about what they don't know. And so if you did it on Tuesday, it would give you a chance to ask very specific questions based on what you know or don't know. I'm not saying I disagree. Whatever, well, let's do that. Who wants it to be on Thursday? Who wants to be on Tuesday? I got to do another poll. Because in the class, it's even Steven. Let's see, let's close that one and do another poll. Where did my polls thing go? Oh, polls quizzes, there we go. All right, so review. It'll be either Thursday or Tuesday, which is the day before the exam. All right. Please answer. You want it to be this Thursday or the day before the exam? The online folks on the side, because it was split pretty even. I think it's going to be Tuesday, right? Because you can see 5 out of 8. There's only one person that hasn't voted, so that makes it 4 out of 8 for Thursday. And yeah, so it's by one vote. It'll be the Tuesday before the exam. I'll see if I can get one ready. I'll try. Yeah. Okay. I'll share the results just for people so that they know I'm not being crazy. All right, that's all I had. Have a great day, everyone, and I will see you soon. Take care.
Hey, Paul,
Oh, you have a question, Riley? Go ahead.
lab tomorrow?
I can't hear you.
Lab tomorrow?
There's lab tomorrow, yes.
Okay, thank you.
I can't hear you. Okay, perfect. Right. Thanks, folks.
Have a good one, Paul.
Bye.
Thank you all.
Thank